Hello, my name is Gian, and today I'll explain why WebAssembly is the game changer of the web. So we'll start with a very short, brief history of the web and JavaScript. So web pages was initially only used to display static pages that link to different, more static pages. Then Netscape came and introduced a new language called JavaScript in 1995 by Brendan Eich to add interactivity to these static pages. Some interesting thing to note is that it only took Brendan 10 days to come up with the initial spec of JavaScript. So that sort of explains the issue that we experience with the language. But it's interesting. So it was initially called Mocha, and then LiveScript, and then finally JavaScript, and it won the battle over all of the other languages such as ActionScript and Silverlight and Flash. So as we know, JavaScript is the programming language of the web. It is an interpreted language, and it is dynamically typed as most scripting languages. So it allows for the following to happen. So you can initialize a variable as a certain type and then declare that variable to be a different type later on with a different statement. And as we know, this severely affects the performance. Dynamically typed languages performs much slower than statically typed languages, such as C and C++. So without information on the type of the variables, it also delays the compilation process as it has to guess the correct type for each variable. But it does add flexibility to the language. So if we look at the JavaScript engine, it's similarly to the Java compilation process, but we don't share source code. So when you open the browser, since JavaScript is an interpreted language, the source files that you download has to be tokenized, parsed, and then only can it be executed. So as we see here, the baseline compiler compiles the source code into an intermediate representation called the bytecode, which is then passed to the interpreter, and which converts it into binary machine code, which is then eventually run on the CPU. This is an extremely expensive and lengthy process, and it's the root cause for JavaScript's poor performance. So Google went and designed a new JavaScript engine called the V8 engine, and they introduced, in order to mitigate the performance drawback, they introduced two new components. The first is called the full cogen. So it's a baseline compiler that produces machine code very quickly. So the idea is if we provide faster application bootstrapping, even with unoptimized code, the execution of the final application becomes quicker, which is a reasonable rationale. Then the second component is an optimization compiler called the crankshafts that takes this source code and produces optimized machine code, and then replaces parts of the machine code with this optimized code over time. So over time, as we run our application on the web, it'll become faster and faster. So this is a good solution, but it still produces additional CPU overhead. This crankshaft still has to occupy CPU time of its own. And then at the end of the day, it still resulted in fairly slow performance. So in comes WebAssembly. WebAssembly is a new type of code that can run in modern browsers and provide new features and major gains in performance. It is not primarily intended to be written by hand. It is meant to be a compilation target for source languages such as C, C++, Rust, to enable them to be ported to the web. It provides a way to run code written in these multiple languages on the web at near native speeds. And so WebAssembly works in modules, and it can be imported in a web or, and this is quite interesting, or a Node.js app. So you expose WebAssembly functions through the use of JavaScript still. If you look at how it works and how it fits into the V8 JavaScript engine, so we have the WebAssembly file comes in as a binary format that is then compiled into bytecode and immediately into machine code, as we see here. So the WebAssembly file is an optimized binary set of instructions. And it's very interestingly, if you look at the end, yeah, after the interpreter and after the turbofan, it works alongside JavaScript. So it shares the runtime of JavaScript. It doesn't disrupt. It's not on its own. It works very. It's very compatible with the existing native JavaScript structure. So this is improves the performance nearly doubles the performance. So the goals of WebAssembly is to be fast, efficient, and portable. It executes at near native speeds with this new structure. So, and also it's platform agnostic. So the currently supported languages are C, C++, Rust, C#, F#, Go, Kotlin, Swift, and Pascal. So we can see the main idea around WebAssembly is to provide a tool chain and support for these languages. It is meant to be a compilation target at the end of the day. And it's supposed to be readable and debuggable. So there is a human readable text format of WebAssembly, of that WebAssembly binary file, which I will demonstrate in a moment. So this file has a one-to-one correspondence with the text representation and the instructions. So this text format allows one to write, view, and debug the code by hand. So it is possible to WebAssembly by hand. Then the goal is also to be kept secure, so it runs in a sandboxed environment, and it does enforce the browser's same origin and permission policies. So it's slightly more secure than JavaScript. So, and also it doesn't break the web. So it plays, as we saw in the diagram, it plays very nicely with JavaScript and the existing web technologies, and it maintains backwards compatibility. So if you consider JavaScript and WebAssembly, WebAssembly is different from JavaScript. It is not intended to replace JavaScript, but to complement the features of JavaScript. So web developers can benefit from both languages. So if you look at JavaScript, it's a very flexible and expressive language. You can definitely benefit from it being dynamically typed, and there's a huge ecosystem with powerful frameworks and libraries that are very mature and has a very large community behind them. And then WebAssembly is a very low-level assembly-like language. It's very compact, it has a compact binary format. So if you download a binary file, that's much quicker than downloading a source file, since the files are smaller, since a binary file is smaller. So already you're benefiting from quicker download speeds. Then once it's downloaded, it runs at near native speeds. So so you're benefiting twice already. Then if it runs, it provides languages with low-level memory models such as C++ and Rust with a compilation target. So manual memory management is still possible with if you're working on the web. So if you move on to the key components of WebAssembly, WebAssembly works in modules. A module is a binary that has been compiled by the browser into executable machine code. So a module is stateless, so like a blob, and it declares imports and exports like an ES 2015 module. And then there's the idea of memory. It's just a resizable array buffer that contains linear array of bytes to read and written by WebAssembly's low-level memory access instructions. Then there's a table. So this is it's just a resizable typed array of references to functions that could not be stored as raw bytes in memory. So it's just the things that couldn't be handled by using the existing memory idea. So then an instance is a module. It's just an instance of a module. So it's a module that has a state. So the state can be anything that's in the memory, the table, or the set of imported values. Okay, so if you look at how we run WebAssembly, you have, let's say you have this function in C or C++. You compile that function into the WebAssembly binary that we see on the right, top right. So then once you have this file, .wasm file, you request that in your client JavaScript that runs in the browser. So then as an array buffer, then once you've got that, you make an instance from that. So as you see the fourth line, you say this WebAssembly.instantiate wasm buffer. The WebAssembly is a global object that's available in browsers that support WebAssembly. Then once you have that instance, you can use the export property of that instance to access all of the functions that has been exported inside of the .wasm file. So I can make my demo. So what I'll demonstrate is exactly how you go from C to the .wasm, and then you request that in your JavaScript. So let's say I have this Fibonacci function. Okay, so it's very simple. It calculates the Fibonacci number of the nth Fibonacci number. This is a very performant or expensive function to because it uses recursion. So if we take this function, then if we use a so there's the WebAssembly Explorer, which compiles C++ code into WebAssembly. You can also use the M script, but it's more complicated and for these demonstration purposes. So if I copy my code here and press on compile, you have what is known as the WAT. So this WAT file is the one-to-one correspondence with the .wasm file. So everything in here, all of the symbols can be translated into, the only needed step is that it needs to be translated into binary. So it's as close as you can go to the CPU as to the metal, possibly. So if you click on, so then if we download this, you can see it downloads as a test file. I've already done so. So this is the file that I've downloaded. So it's binary. As you can see, it can't be represented. So then, so I have a small web project open. So it's a very simple index.html. I'm not doing anything interesting here. I'm only using my script. I'm only importing my script, which is over here, which is main.json. So what I'm going to do is I have the Fibonacci function implemented as a JavaScript function, and then I'm going to request this .wasm, which has the Fibonacci function implemented in C, and then I'm going to show the difference in time, in execution time. Okay, so onto the demonstration. So this is my, if I reload, so then it runs the Fibonacci of 45, and it takes, you can see it takes 4 seconds. Then it runs the same function, Fibonacci of 45, and you can see it's almost double. It nearly takes twice as long to run the same function. We can run it again. So that's the C version, just to, so it's still C. Yeah, so it's so it's nearly twice as so using normal native JavaScript is nearly twice as slow as using WebAssembly. What I've also done is I made a native, so a C program that I'll run on my machine now, just to show you what native speeds are to compare. Okay, well, yeah, but I think the time is very similar to, yeah, so it's nearly 4 seconds if you run it on native, if you run the C on native. So then finally, I'd just like to mention the support. So currently at this stage, you only have, it's only Internet Explorer which does not support WebAssembly. So there's really, even though there still has a lot to be done, the possibility exists to harness and exploit this technology, given that this massive amount of support that we have. Yeah, but thank you, yeah, for listening to my talk.